Working models are the tools with which an engineer can assail a problem that cannot be evaluated by known theories or measured and gauged due to the enormity of the project. Models provide probable designs, confirming the adequacy and feasibility of a plan. Even though the models in many cases do not appear as an exact replica of the project being studied, they are constructed to obey the same physical laws that the prototype abides by.
Then, through a new marvel of science, he learns safely on the ground the most difficult of all the pilot's tasks, to fly by instruments alone. In the blind link trainer, listening in his phones to the instructor's directions, he acquires the personal skill that will one day enable him to fly 600 miles over a darkened Europe to Germany.
You will now do a spin. Close the throttle. Move the control column fully back and apply full rudder. Look out, there's rough weather ahead. Keep your airplane straight and level.
In the same way, his instructor teaches him to use the Lorentz beam, which will guide him to a safe landing in England when fog and blackout have hidden his home field. The interrupted note tells him that he is coming into the path of the beam to take up his true course. Carefully, he crosses the airfield, turns, and comes down for a blind landing. It looks easy, and so it is to the overconfident. But one instrument, the altimeter, escapes his eye. He forgets that he is losing height too fast. Pilot dies horrible death.
The Mercury capsule project is the nation's manned orbital spaceflight program being conducted by the National Aeronautics and Space Administration. The project involves a continuing, broad research program. The Mercury capsule shape was determined from intense scientific and engineering investigations using a wide variety of technical equipments. The moment of inertia on test models was determined on this pendulum rig. Wind tunnel tests of small and large-scale models have been carried out, covering a speed range from 0 to 18,000 miles per hour. Small models of the capsule were fired in this supersonic free-flight ballistic gun range. In the gun, helium compressed by a powder charge accelerates the 1-inch model down a 30-foot instrumented range of recording stations. The model achieves speeds of up to 10,000 miles per hour. Data are recorded by means of special cameras located along the length of the range. As the model speeds down gun range barrel, graphs and shadow graphs are acquired. This shadow graph, taken at one of the recording stations, clearly shows the flow of air passing around the model at supersonic speeds. Detailed analysis of data acquired in tests of this nature provide a solid basis for proceeding to more complex tests and to improved versions of the capsule shape. In other tests, a small model was instrumented to measure the scorching heat of re-entry as simulated in a shock tunnel. The air in this tunnel rushes past the model at 14 times the speed of sound. The severe heating ionizes the air in the region of the heat shield, causing it to glow. In another wind tunnel facility, free-falling models were used to determine the best attachment points for the parachutes. And a detailed picture of the flow of air over the capsule at relatively low speeds was obtained by observing the movement of pieces of yarn glued to the surface of the model. Full-scale capsule models were tested in a large wind tunnel to determine the capsule's lift, drag, and pitching moment characteristics. The validity of the Mercury configuration had to be established not only for the capsule alone, but also for the capsule with the escape tower. In a typical wind tunnel experiment, a scale model of the escape configuration was tested over the speed range from 1 1/2 to 4 1/2 times the speed of sound. During the test, the model was forced to oscillate to determine its dynamic stability characteristics. In other tests, the effect of the Mercury capsule on the performance of the various boosters to be used in the program was investigated. The static stability of the capsule fitted to an Atlas booster was determined in a 9 by 7 foot supersonic wind tunnel. Wind tunnel tests were of particular importance in the case of the Redstone booster. The Redstone is an aerodynamically stabilized vehicle, as is evidenced by the large tail fins. In these tests, it was determined that the booster would coast along a stable path, even if the rocket engine was suddenly shut down. The stability of the Little Joe booster with the Mercury capsule and escape system installed also had to be established. In the wind tunnel testing program, Mercury experiments were performed in 26 different wind tunnels of the National Aeronautics and Space Administration and of the Armed Services. 70 separate models of various sizes and configurations were constructed, and 106 tests were conducted. In each of the 106 tests, a number of variables, such as Reynolds number, Mach number, and angle of attack, was investigated. But wind tunnel tests alone are insufficient to solve all of the many problems associated with the Mercury flight system.
This Project Mercury candidate is preparing for stress. The weight of 8 gravities will thrust upon him as he rides the human centrifuge. His reactions are studied. The results will indicate how he fared under multiple gravity forces. Did he show a tendency to pull back? No. Was his tolerance level low or was it high? Now, can we shake his equilibrium? How does this affect his pulse and blood pressure? And what about his mental balance, his imagination, his personality, motivation? How does he see the different problems of living? And how has life affected him as an individual? Test his memory, comprehension, perception, visualization. Ask him to describe himself in 100 different ways with a battery of tests. Now take him up to 65,000 feet for 1 hour in a pressure chamber. Now have him do this for 5 minutes. Then ask him to take a walk. Walk until his heart beats 180 times a minute. Elevate the incline 1 degree every minute. These tests continued until all 32 men had been evaluated. Seven men emerged from this competitive purgatory as the Project Mercury astronauts. At McDonnell Aircraft, they saw a model of the space capsule they would ride into orbit. They sat in the cockpit for the first time. This is the beginning for each of them. Captain Donald K. Slayton, United States Air Force, age 35, from Sparta, Wisconsin. Lieutenant Commander Alan B. Shepard, United States Navy, age 35, from East Derry, New Hampshire. Lieutenant Commander Walter M. Schirra, Jr., United States Navy, age 36, from Wardell, New Jersey. Captain Virgil I. Grissom, United States Air Force, age 33, from Mitchell, Indiana. Lieutenant Colonel John H. Glenn, United States Marine Corps, age 38, from New Concord, Ohio. Captain Leroy G. Cooper, Jr., United States Air Force, age 32, from Carbondale, Colorado. Lieutenant Malcolm Scott Carpenter, United States Navy, age 33, from Boulder, Colorado. These officers were detailed by their services to report to the NASA at Langley Field, Virginia. Here, the National Aeronautics and Space Administration Space Task Group, under the direction of Robert Gilruth, had organized a training program for the astronauts. They were excellent students, and they had a realistic and tough-minded approach to Project Mercury. They had to know all the answers. Here, they discussed the flight tests. In the flight program, they would ride both the Redstone and the Atlas boosters. But a man would not ride either booster until the full test program was a success. The schedule included first instrumented capsules, then capsules with a monkey aboard, and then one of the 7 would go into space. The schedule also provided for the problems of flying near the Earth. They must maintain their proficiency in high-performance military aircraft. Out of this training together, a strong esprit de corps developed. They all felt that this must be a team effort involving all of Project Mercury. Recognition would undoubtedly go to the man who makes the first flight. But the second, third, or fourth flights may produce far more scientific information than the first flight. Soon, all of the astronauts were busy qualifying themselves for space flight. They rode the human centrifuges of the Air Force and the Navy. Here, they trained to increase their resistance to the forces of nature that were pitted against them. But each new experience, each small physical or mental victory was backed up by hours of classroom work. The time had come to select the pressurized flight suit they would wear. All of the suits tested were air-conditioned, had an attachable helmet, and would protect the pilot from heat and from the deafening 155 decibel noise of the blastoff. The problem was to select a suit which had complete pressure integrity, which was resistant to temperature and was not too bulky, a suit which allowed comparative freedom of movement, yet a suit which was completely reliable. This modified U.S. Navy Mark IV suit worn by Shepard was selected for further testing. To get the feel of space flight controls, this trainer at NASA's Lewis Research Center in Cleveland demonstrates the possible motions of a capsule in space.
As the training program progresses, the development and production of special flight equipment has continued. Each astronaut has been fitted with a custom-made couch developed to support his entire body and reduce the physiological effects of high acceleration forces, or Gs. To make the couch, the astronaut is placed in a bed of special quick-hardening sand. After the sand is carefully packed around the astronaut's body, carbon dioxide is applied to speed up the hardening process. At the end of the 2-hour-long couch molding process, the astronaut is carefully lifted out of the mold. These Mercury couches were produced at NASA facilities with painstaking care to assure proper fit and effectiveness in protecting the pilot during flight. During re-entry into the Earth's atmosphere, the Mercury capsule will be subjected to intense frictional heat. One of the early practical training activities for the astronauts provided familiarization with high heat conditions and the ability of the ventilated full-pressure suit to keep them cool under these conditions. This heat chamber is capable of producing the same temperatures anticipated inside the capsule during the re-entry from orbit. Quartz tubes along the outer walls provide the chamber with heat. In this test, the pressure suit ventilation system was turned off to familiarize the astronaut with his own physiological reaction to short periods of high heat. In Project Mercury, the pilot will play an active role in the operation of the Mercury satellite. He will be able to control the capsule's attitude. He can maintain current knowledge of his position visually and through the use of radio navigational aids. He will be able to operate all primary flight controls, such as the firing of the retro rockets to begin his descent toward the atmosphere and to deploy the parachutes once he has re-entered the atmosphere. Wherever possible, the capsule's flight performance is simulated on the ground to provide realistic, economical training for the astronaut. In this fixed-seat analog simulator, instrument readings indicating a simulated capsule attitude are supplied by an analog computer. The pilot responds to the instrument readings by applying the proper control movements with the sidearm controller. In flight, this controller would activate small reaction jets to turn the capsule about its 3 primary axes. On the simulator, the control movements feed signals to the computer and result in changed instrument readings, portraying the kinds of capsule attitude changes which would have resulted from control movements in flight. Training on such simulators, the astronaut developed skill in maintaining the capsule's orientation during orbit, retrofire, and re-entry. Following the indoctrination on the fixed-seat static simulator, the pilots will be trained on a dynamic simulator. On this device, the astronaut will be supported in a molded couch. His sidearm controller will be connected to a system of reaction jets similar to the ones in the Mercury capsule. These jets will rotate the couch or pitch it up, down, or sideways. An intricate system of motion picture displays will give a view similar to that seen by the pilot in orbital flight. A special feature of this simulator is a low-friction air bearing designed to permit movement in all directions around a center post. One of the most important phases of the pre-flight training is that received on the centrifuges at the Wright Air Development Center and at the Aviation Medical Acceleration Laboratory at Johnsville, Pennsylvania. These centrifuges have the capability for reproducing the same acceleration, or G forces, on the same timescale as will be encountered during rocket-boosted launch and re-entry into the Earth's atmosphere. In this training, the astronaut learns more about the effect of these G forces on his ability to perform essential in-flight functions and what he can do to overcome those forces. While whirling around in the centrifuge cab, they learn new techniques of breathing and straining so that they can tolerate these high G forces while still performing functional control tasks. The centrifuge is operated in response to signals provided by a computer. The sidearm controller also gives electrical signals to the computer. These signals are translated into motions the reaction jets would have given to the Mercury capsule in flight. These signals result in changes in G forces within the centrifuge cab comparable to those encountered in actual flight. The test demonstrated that a properly trained man in good physical condition would be able to control the Mercury capsule even while being subjected to the high G forces of launch or re-entry. In other procedural trainers, the astronaut will be checked out completely and repeatedly in all of the procedures and operation of the capsule.
The moon is a unique body. There is no place on Earth that offers a topography quite like it. Certainly, the Earth has features similar to those on the lunar surface. But nowhere is the Earth cratered to the extent and in the same manner as the surface of the moon. Where can men go to test and practice the exploration techniques being developed for Apollo landings? the United States Geological Survey decided to build a model of one part of the lunar surface in an area accessible to present research centers. Examining a multitude of lunar photographs taken by the orbiter satellites, survey scientists choose proposed Apollo landing site 2P6 in the southwest part of Mare Tranquillitatis as a representative area and one that would be profitable to reproduce. Where to build it? Near Flagstaff, Arizona, are fields of volcanic cinders, the result of eruptions about the year 1065. The cinders provide an excellent material to recreate the lunar surface, and the geologic structure will offer training in mapping and sampling for astronauts. Craters on the lunar photos have been carefully examined, and their relative ages charted. All the craters are separated into 3 major age categories, from oldest to youngest. Of the 426 craters larger than 2 meters across that can be seen on the photos, 354 are among the oldest, 61 are of intermediate age, and 11 appear to have been formed recently. An area covering over 268,000 square meters is chosen and fenced off, and construction of the crater field begins. First, the ground is prepared by dragging to clear away the underbrush and to produce as smooth an original surface as possible. It will be important not only that the craters are reproduced in the same size and approximate age relationships as on the lunar surface, but that the material ejected from them creates a surface similar to that on the moon. So all the existing bumps and irregularities are smoothed out. Then a surveying team carefully locates the center point of each crater visible on the orbiter photographs, and stakes are driven to mark the position. Each stake is color-coded so that the craters of the 3 different ages can be identified. Finally, all the craters have been positioned and marked as old, intermediate, or young in age. Placing explosives in holes at the right location and blowing them in the right order to match the age sequence is not all that is required to recreate a portion of the moon's surface. The composition of the cinder and clay material is carefully studied to determine what size charges to use and how deep to bury them, so that each crater will be, as nearly as possible, the same size as its lunar counterpart. After weeks of study and calculation, these values have been computed for each of the 426 craters. We are ready to dig the holes. As the backhoe slices into the ground, it exposes the variety of materials that make up the cinder lake. Cinders from nearby craters have fallen over the area at different times. Between some of these pyroclastic episodes, brown clay was deposited. The result is layers of clay and layers of cinder from different eruptions. In some places, the cinders fill pockets in the clay. Great care is taken to dig the holes at precisely the depth calculated by the explosives expert. As the appropriate depth for each charge is reached, the last few scoops are removed one at a time, and measurements taken between scoops. Now that the different layers of geologic units are exposed by the backhoe, a geologist can conduct a detailed stratigraphic study in the deepest of the charge holes. The result of his study will be a control on geologic traverses conducted here. During most testing of lunar procedures, the test subjects have not previously studied the area. Besides testing techniques and tools, they attempt to define the geologic formations in the region. So this geologist carefully describes the different layers, their thickness, their composition, a valuable check on the accuracy of the test subject's geologic analysis. Not only are we creating an area that very closely resembles a portion of the lunar surface, but an area which should present geologic problems analogous to those an astronaut will encounter on the moon. Once the geologist has completed his work, the final preparation of the field for explosions can be made. 426 holes await the emplacement of explosives. Boosters are prepared, which will be used to set off bags of nitrocarbonitrate. Each hole is loaded with a size charge calculated to create just the right size crater. The bags of explosives are positioned with care and the boosters inserted. Primer cord is attached to the boosters and held out of the way while the hole is filled. One after another, all the charges are laid, even though different craters will be fired at different times. 426 explosive charges, 426 craters in the same position and of the same size as one part of the moon's surface, if the amount of explosive has been correctly calculated, if the depth of each crater is correct, if the surveyors have accurately reproduced the crater positions. Finally, all the explosive charges are in place, and the holes have been covered over. Once more, the field is dragged back and forth until it is smooth again. All that can be seen are stakes marking the position of the primer cords. One by one, 354 of the charges are tied together and the stakes removed. These will be exploded first. The ejecta and debris will spread out over the surface to be covered by later explosions, and so they will represent the oldest craters in one part of the moon. Primer cord is a unique firing device. Connecting all the charges to the firing box, it burns with such speed that a piece of it laid across the country would burn out in Los Angeles only 13 minutes after it was lit in New York. One after another, all the charges to be fired in the first shot are tied together. Several months have gone by since this area was selected and fenced off. Hundreds of man-hours have gone into the calculations and careful preparation for firing. And now we are ready. Give us 354 old-age craters.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire!
Now we need 61 craters of intermediate age. Here's the same detonation recorded by high-speed cameras rolling at 5,000 frames per second. They show the primer cord tracing paths to each of the 61 shot holes. Later, the 11 youngest craters are exploded. As each set of craters has scattered debris over the surface, we have created an altogether new geologic area, with the oldest ejecta on the bottom and the newest on top. In some places, the original layers of cinder and clay have been completely turned over. We have changed a rolling cinder field into a crater field. But how closely does it match the topography of Lunar Site 2P6? This is the orbiter photograph of the lunar surface. And this is an aerial photograph of the new crater field. The size and location of each of the 426 craters have been reproduced with remarkable accuracy. On this crater field, astronauts will be able to train in a more realistic setting. A setting like the lunar surface. A little of Mare Tranquillitatis here in Flagstaff, Arizona.
This is Grover, a simulated lunar roving vehicle that is used to develop procedures and to identify problems associated with geologic exploration of the moon. It has been driven by the astronauts to familiarize them with the operation of an actual lunar roving vehicle, or LRV, and to rehearse them for their geologic assignments during lunar surface missions. Because of limited life support systems, astronauts on foot can only go a distance of about 2 miles from the landing site. With an LRV, however, the radius of their exploration can be expanded to about 6 miles, permitting the collection of a much larger sample from the lunar surface. Grover was built in a special vehicle shop at the U.S. Geological Survey's Center of Astrogeology in Flagstaff, Arizona. R.A. Mills, who supervised the construction of Grover, explained some of its features.
This is our simulated portable life support system. It takes up the space at the back of the seat that the real life support system occupies during short sleeve tests. Located beneath the seats are special wire-reinforced cloth storage bags. These are to be used for storage of geologic samples and other small pieces of equipment. Basic navigation information is provided through a gyroscopic heading indicator. This is periodically updated through a sun alignment device. Communications are handled through this low-gain antenna. This is adjustable from the seated position. In addition to a seat belt as a restraining device while driving on the lunar surface, extra security is provided through the use of Velcro fastening material. These patches are attached between the back of the portable life support system and the back of the seat. These make it slightly more difficult to egress from the vehicle. Breakaway from the seated position is aided by the use of an outboard tow hold. Should failure of a drive motor occur, the outboard tow hold may be withdrawn from its socket and used as a decoupling tool by insertion into the drive mechanism. The Lunar Communications Relay System contains the power supply and the control systems for the colored television camera and the antennas. Aiming of the S-band antenna is a manual operation using this optical device for alignment. While the vehicle is parked, and after initial alignment of the S-band antenna, the colored television will be remotely controlled from Earth to observe the astronauts on the lunar surface. Mounted on an extension of the right handhold is the 16mm data acquisition camera. This camera can be operated from the seated position. Primary drive power for the rover is provided through 4 standard automotive type batteries. Located beneath this case are the steering and driving controls. Power for the control system relays is provided through this 24-volt aircraft battery. For steering, activation of the hand controller sets into motion an electric motor driving this rack and pinion steering gear. Braking of the rover is accomplished through this electric over hydraulic device. The rover suspension is independent with torsion bar springing. Drive power is through 4 individual 24-volt direct current motors, 1 for each wheel. Final drive to the wheel is through a gear reduction case in the hub. The hand tool carrier presently fitted to the rover is being used for experiments in geological methods. It does not have the same configuration as the flight-qualified unit currently being developed for the lunar mission. To activate the rover for driving, the first step is to turn on battery power. The next will be selecting power for each of the 4 individual drive motors. Next we'll select steering. We have a choice of either normal or crab steering. In this case we'll select normal. And finally the direction of travel, either forward or reverse, and we'll select forward. All of the vehicle control movements are incorporated in a single lever, centrally located so that it can be operated from either seat. Now left steering is, of course, left, and right for the right steering. Brake application is by pulling back on the handle, and forward movement releases the brake and applies power.
Grover will not go to the moon, but it is a valuable tool for training our astronauts to explore the lunar surface more effectively.
In the near future, man will be landing on the moon to explore the lunar terrain, take scientific measurements, erect housing facilities, and prepare the space vehicle for the return to Earth. In performing these tasks, the lunar explorer will find it necessary to adjust his normal methods of self-locomotion due to the moon's low gravity and the restraints imposed by his bulky and cumbersome spacesuit. In order to study the problems of walking, running, and other forms of self-locomotion in various environments where the gravity level is less than that on Earth, a gravity simulator was devised by the NASA Langley Research Center. The new technique permits a subject to perform many locomotive tasks at various gravity levels for extended periods of time and over relatively large distances.
This new technique is based on the fact that the arms and legs move in essentially parallel planes, and that these planes of movement are usually aligned with the Earth gravity vector. Simulation of a reduced gravity field is produced by inclining the test subject relative to this vector so that the gravity component in the plane of movement is equal to the desired value. The inclination angle for simulation of the lunar gravity condition is 9.5 degrees from the horizontal. Zero gravity is produced with a horizontal attitude. Of course, the test subject must be properly supported in these attitudes so that his body members are free to move in their normal manner. This support is provided in the Langley simulator by a series of slings and cables attached to a lightweight crossbar supported from an overhead trolley unit. The trolley is moved along a monorail track so that it stays directly over the test subject as he moves back and forth along the walkway, which is parallel to the track. The desired gravity level is obtained by adjusting the displacement of the walkway from directly beneath the track. The following scenes illustrate the operation of a working model of this simulator and illustrate the ability of one test subject to perform a number of tasks in the simulated lunar gravity condition.
The subject is supported at the buttocks, the upper torso, the head, and the calf of each leg. The tubular frame used for support of the lower leg provides freedom of movement for the upper leg. Sometimes a sling for the lower arm is used, depending on the type of test being made and the preference of the subject. The subject is very comfortable in this position and can move his body in a normal manner, even though restrained from lateral movement. The monorail is 40 feet above the floor, and the length of the cables attached to this trolley is about 37 feet. The walkway is 24 feet long for these exploratory tests, but can be extended up to 250 feet for a more extensive test program. In order to show a continuing comparison of locomotion at both lunar and Earth gravity conditions, the camera was oriented to make the subject in the simulator appear to be in the vertical position, and a split frame camera technique was employed. On the right, in starting and stopping his movement due to the low foot traction resulting from the subject's low apparent weight. Similar difficulty is encountered by attempting to run. The degree of difficulty will vary with both the type of footwear and the type of surface used on the walkway. When a load of about 60 earth pounds is carried on the back, the subject finds some of the tasks easier to perform due to the increased traction on the walkway surface. Climbing steps is no problem when done at a slow pace. Difficulty in coordinating the feet is encountered, however, when attempting to climb at a faster rate. The same problem. Climbing a pole under the lunar condition by use of one hand. For Earth gravity tests, vertical jump distances of about 2 feet and a duration of 1/2 second can be obtained. For the lunar gravity condition, the subject can jump a distance equivalent to about 14 feet with a duration of 4 seconds. However, the subject has difficulty in maintaining balance throughout the jump because of small amounts of residual angular momentum that are not a problem for the Earth gravity condition. In cases of falling from heights up to the maximum jumping height of 14 feet, there is little risk of injury because of the relatively low impact velocity and the long duration of the fall, which permits the subject to prepare for the impending contact. A number of gymnastic feats can be performed by the subject, which can be performed only by experienced gymnasts under Earth gravity conditions.
Many tests, similar to those you have just viewed, have been made using numerous test subjects of various sizes and stature, and the feasibility of this new gravity simulation technique has been established. Several applications for this new research tool are apparent. For instance, this technique will be useful in the development of an efficient spacesuit, which will provide protection from the lunar environment with a minimum of restraint on the man's locomotive capabilities. The use of auxiliary devices such as a rocket jump pack to assist the lunar explorer can be evaluated. Furthermore, the design, development, and erection of lunar base and space station facilities will be aided by extended studies utilizing this technique to determine the limits of man's capabilities under various gravity levels. These studies will also aid the planning of logistics support for various space missions. And finally, the simulator can aid in training the spacemen by letting them experience the sensations and effects of unaccustomed gravitational forces encountered in space exploration. Without the high-speed computers which the manned space program helped develop in the 50s and 60s, there would be no manned space program. We could not have orbited the Earth. We could not have landed men on the moon. Let us see why. The environment of spaceflight is full of unearthly complexities. Intruders in space must cope with solar and cosmic radiation, with extremes of heat and cold. Meteoroids, weightlessness, vacuum, silence, and infinity. Before flying off into such a different environment, we require carefully designed spacecraft to carry life support systems of air and pressure. We must provide for food and water, waste disposal systems, protective structures, and energy systems for electric power and propulsion. Computers play an important role in the design, manufacture, and testing of all such systems. To minimize costs and maximize safety, spaceflight systems and requirements are first simulated by computers. In this way, for instance, hundreds of multi-million-dollar manned moon landings were made before the Apollo lunar landing spacecraft was built. For comparatively little, essential engineering data were derived and safety measures were tested without risking lives. In planning a spacecraft, some of the most important components designed are the onboard computers. This is because many of the solutions and decisions we face as we travel in this new ocean of space are beyond the problem-solving capabilities of men unaided by computers. For example, if we are orbiting the Earth or the Moon and wish to rendezvous and dock with another spacecraft flying several miles ahead of ours, large numbers of complex flight computations must be made almost simultaneously. To change our orbiting speed for rendezvous, computers are needed to fire the spacecraft's propulsion engines. To change our attitude for docking, they must fire attitude control thrusters, often in bursts measured in tiny fractions of a second. The rendezvous and docking maneuver is just one of many spaceflight phases containing far too many variables for a man alone to compute and apply in the time available. Computers, both on board the spacecraft and on the ground, are indispensable in keeping track of the details of spaceflight dynamics and navigation, predicting relative positions, and monitoring remaining fuel and other consumables, as well as firing thrusters and engines as needed. Long before a space mission is launched, the parameters of the mission must be calculated with the help of high-speed computers. Optimum design of the mission profile and the spacecraft can be predicted by the computer in advance using theoretical data. Scientists and engineers present their problems in the form of mathematical models to the scientific computing specialists or computer programmers, who translate the math into computer language. This coded math is punched on cards as instructions to the computer. Also, data related to the design problem are encoded, converted to some form the computer can read. One of these forms is the punched card. The information often is transferred from the cards to a magnetic drum or tapes, which can be read by the computer. Problem solutions by the computer can be displayed in various ways. A cathode ray tube, like a television picture tube, may display design solutions which can then be photographed on the face of the tube. Lunar landing of a three-dimensional lunar module. Rendezvous of the lunar module with the command module. Earthrise over the moon.
star fields for use in navigation. All of these computer-generated animated drawings were made before the first Apollo manned lunar mission. The computer has since been proved right by history. Another area of computer-assisted engineering involves the processing of data from actual tests, as distinguished from theoretical predictions. For instance, consider the immense amount of aerodynamic, thermal, and metallurgical data in the re-entry of a spacecraft through the Earth's atmosphere. This was the first re-entry test of an Apollo command module. It was unmanned, but recorded by automatic onboard cameras. Approaching the Earth on its return flight from the Moon, the spacecraft reaches a velocity of 25,000 miles per hour. As it slams into the Earth's increasingly dense atmosphere, temperatures rise to several thousand degrees Fahrenheit. Due to the blunt shape of the command module, most of this heat is dissipated by waves of air molecules which form and act like a bumper, pushing other molecules of air around and away from the spacecraft. The heat shield must cope with 5,000 degrees of heat as its ablative surface material crumbles, gases, and chars the heat away. Inside the cabin, temperatures remain comfortable. In this first flight test, telemetry relayed the data to a ground tracking station. The station recorded the millions of bits of data in electronic form on analog tapes. The tapes were rushed to the manned spacecraft center, and the data were transferred to digital bits on other reels of magnetic tape. These were then run through the computer. In this case, the computer's output was by a high-speed line printer. After analyses and application, the output data were photographed on microfilm and placed in storage for future reference. So voluminous are such records that another small computer is required to index them and retrieve them when they are needed. Just as spacecraft and systems must be designed, built, and tested over years of research and development with the help of computers, so the men to fly the spacecraft must be carefully prepared and tested. Their every psychophysiological characteristic must be known, analyzed, and evaluated for the responsibilities they must assume during a space mission. From regular and special medical examinations, from biosensor monitoring of each man in a variety of activities, including actual space missions, a store of biomedical and behavioral data is maintained by the computer, capable of rapid retrieval and analysis on that man's suitability for a particular assignment. The pioneering work done in this area at the Manned Spacecraft Center may have far-reaching impact on future computer usage in general medical practice. Astronauts also must spend hundreds of hours in simulators going through every phase of a mission in every nominal and contingency condition imaginable. Training simulators would be inadequate without high-speed interpretive computers, which are used to simulate operational spacecraft computers long before a particular space mission is undertaken. For astronaut training programs, systems planning engineers design both the hardware and the software to make the simulators very realistic. In the Apollo Command Module simulator, most spacecraft systems are represented. Digital computers perform real-time computations that put trainees into convincing spaceflight situations. The sense of reality is heightened by simulated spacecraft characteristics, flight dynamics, and visual and sound effects from control panel lights to jet and rocket noises. The Lunar Module Simulator is also an all-digital simulator with 3 computers using coordinates based on math models to simulate the spacecraft and the lunar landing phase of a mission. As in the command module trainer, simulation of the primary guidance, navigation, and control system is a most significant part of the training procedures. In the lunar module itself, the controlling element in the system is an onboard digital guidance, navigation, and control computer.
Dial your code numbers. Keep receiver off open. There will be no comp check.
By the time a manned space mission is launched, flight crews and ground support crews have flown the mission hundreds of times, thanks to the computerized simulators. Pre-launch checkouts at the Cape involve many weeks of computer-assisted countdowns. The launch itself would not otherwise be possible.
10, 9, 8, ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commit. Liftoff. We have liftoff.
At liftoff, as the spaceship clears the tower, the Mission Control Center in Houston takes over command of the flight. The flight director's most valuable resource is the real-time computer complex, one of the largest computer assemblages in the world. Here is some of the computing equipment that calculates flight paths and solves other problems of the space mission on a real-time basis. When necessary to keep the guidance system up to date, the solutions are transmitted to the spacecraft and fed into the onboard computer. Computer-driven data displays reveal the spacecraft's quickly changing location, velocity, and other conditions derived from tracking the spacecraft and communicating with the crew.
Roger, the S-band pointing is pitch minus 22, yaw plus 8. Bird time is 10.3. Roger, Houston.
The actual landing on the moon depends on computerized readings of remaining fuel and altitude.
50 feet. We're in good shape, too. 3 feet per second. 40 feet. 3 feet per second. 30. 3 feet per second. Looking great. 20 feet. 10. 3 feet per second. Contact now. 2. Stop. Brake. Pro. Auto. We're on the surface.
While on the moon, astronauts perform active seismic experiments and emplace scientific instruments such as seismometers, magnetometers, and ion particle detectors. Voluminous data are transmitted to Earth from these instruments, which make up the various stations of the moon's expanding science network. The data are interpreted with the help of computers. After a mission returns safely from the moon, computers are also indispensable. Inside the Lunar Receiving Laboratory, moon rocks and soil brought back by the lunar explorers are studied and subjected to preliminary analyses with the help of computer-controlled instrument systems. Remote terminals are set up to permit the antiseptic removal of data from the laboratory and to enable the investigators to use outside computers in their work. Computers are used to identify and classify moon matter and to reduce the data detected by such lunar lab instruments as radiation counters, gas analyzers, mass spectrometers, and electron microscopes. Information processing at MSC is not all related to the moon and outer space. Systems also are devised for the most efficient business management of the center, whether it be a computerized system to record, remember, and report on books checked out at the technical library, or the computerized magnetic tape library of more than 40,000 tapes. Other computerized operations at this remarkable one-of-a-kind city of space control and prepare paychecks, warehouse inventories, and even inventories of scientific and technical skills to ensure the fullest utilization of the space program's most valuable asset, its people. Another program using computers at MSC is that of Earth Resources. This program uses aircraft to test and develop cameras and other sensors in studies of the Earth. Photo enhancement and pattern recognition of data gathered from such flights are two computerized techniques. The computer draws and color codes various crops growing in a large mapped area of the Earth's surface. Corn, rye, and barley are shown. Similar techniques are used to reveal areas of plant disease, forest fires, underground rivers, and other surface phenomena. Earth resource studies by aircraft and computers are valuable today in their own right and are also contributing to the development of scientific tools for vast studies of the Earth, the Moon, and the planets by manned spacecraft of the future. Skylab, space shuttles, space stations, and eventually spaceships to carry men to Mars. The computers at the Manned Spacecraft Center are truly our keys to the future.